Alright, good to see everybody, and I know this video is long overdue, and that's because the robot project itself, I've discontinued it. I didn't have the time to continue developing it, so it just sat in the corner for quite a while, and then I actually sold it to someone who wanted to continue it and who wanted to explore it. But over the past months, there's been an increasing interest about this project, and people have asked about this control software. So I thought I would make a quick explanation on what kind of programming code I used to control this robot. And I am in no ways a software developer or a coder, so if somebody's into that, this probably looks awful to you. But this is what I did and how I got it to work, kind of. And it consisted of two separate programs. So there's Visual Studio, Microsoft Visual Studio, that you've got here on the screen. And this was the GUI that you used to control the robot. And then you'd have an Arduino code running on the Arduino and actually controlling the stepper motors and the stepper drivers. Right, so let's first go through what's in here. So this is just a kind of a simple GUI controller, and it's sort of being mimicked around the Universal Robots controller. I used those quite a bit, so just kind of on the top of my head, I threw some similarities in. And basically what you have here is different connection and enabling and calibrating stuff on the left. Then you have the jogging and driving in the middle, and then there's a photo representation of the axes that correspond to joint numbers, as well as speed and acceleration sliders and a couple of waypoints and a plate. Right, so let's start from the left. So there's a drop-down menu on the connection. This would just choose the correct port that the Arduino is connected in. So the Arduino was connected on the computer through a USB connection, and this would just be that port. And you choose the port that had the Arduino in it, and then click connect, and it would show you on the connection status. It would turn into a green on sign if it was connected properly. Right, so this enable joint 1 to 6. All these would do is enable the stepper drivers so that there's current on the stepper motor, because if you use stepper motors, you know that there's a enabling pin that you can write high or low, and that basically just changes whether or not the stepper motor is getting current. So this was done basically just to be able to control different axes, because when I was developing this, I didn't need all the axes and I didn't have all the axes ready. So I created this bit of code to be able to turn off all the other steppers but the one that I needed when I was testing. And that's just because of the stepper motors and their tendency to heat up when they are turned on. So if they are under holding power, they're heating up. So this wasn't the easy way to turn them off. And obviously here you have enable all, disable all. That would just tick all the boxes or empty them. Right, underneath it we have a calibration method. So this would be calibrate joint 1 to joint 6. You could do all of them individually, or you could auto calibrate all. Now the calibration would actually just, there was limit switches on all the axes on the robot, and what this would do is it would rotate the given axis one at a time towards the limit switch, and once it hit the physical limit switch, it would then start turning the other way, and there was a given number of steps. So it was a different axis where the limit switches were placed on very different positions. So after each axis had hit the limit switch, there was a defined number of steps that that axis had to move, and it basically made a T-pose, or it just turned itself to a sort of home position. Then it would actually zero all the axes, so those would be 0 points, and then you could move to negative or positive side from that point, and it will remember the number of steps. Right, in here, we have the actual jogging, so the moving of the robot. And these buttons right here, so for example, J1 minus or J1 plus, that would move joint 1, so the rotation of the robot base, or either clockwise or counterclockwise. And this would go for all the joints in here. And in between all of them, there is a box, and this would preview the current position of that joint. So this would show the number of steps that this joint is away from that 0 position after calibrating. So for example, this could show you 1,000, and it would mean that it's 1,000 steps on the positive side from the 0 point. And you could also use these boxes to drive the joints to a certain position. So you could give all these boxes a certain value and then click drive joints to values, and that would just drive each of these joints to that given position. But it would calculate the speed that each of the axes should rotate so that all of the moves are completed at the same time. So here we have these parameters, and then you'd have save waypoint 1, save waypoint 2 and 3, and then play. And you can move the robot to a certain position, give it a save waypoint 1, and that would just save all these values to a memory slot. And then you could do it again and again and get 3 different points. And then when you hit play, it would move from waypoint 1 to 2 to 3, and then stop the program. The idea with all of these different buttons and stuff is very simple, actually, the way that it works. So as I said, I'm not a coder, so this is probably not the best way to do it, but this is how I did it. So each of these buttons right here, let's take J1 minus, for example, say a J1 plus button, mouse down. So as long as you press mouse down above J1 plus button, it would take the speed value from the speed bar and then send a string. So it would send a bit of text to the Arduino, which would be jog J1 plus, followed by a comma, followed by the speed value that is read from the speed bar. And then it would write this to a data out, or it would write the data out to a serial port. And what this would do is each time you'd press a certain button in here, it would send a word over to Arduino, followed by any information that it needs. So say speed, or later on it should have sent acceleration stuff. And as long as you kept the mouse down, so these were all private void mouse down. So as long as the mouse is pressed down, it's actually sending this word over, or it sends it once. And once you release the mouse, so if you release the mouse from this button, it would send a string called stop, and that would actually stop the motion. And this way, as long as you press the button, it's moving. And as soon as you let go of the button, then the robot will actually stop. And obviously there are toggle buttons right here, say enable. So these would just, if there is a tick on the box, this would just send over a word, say enable J1. And then if you click it again and it unchecks the box, it will send a word like disable J1 over. And same goes out with these calibrate buttons. Enable all button would send a word called enable all. Disable all would send a word called disable all, and so on. And drive joints to values would actually just check all these boxes and send them in a string. So it would be this number, comma, this number, comma, this number, comma, this number, comma, this number, and then followed by the speed, and then it will send that string over. And this is basically all that this code in here is. And so that's basically this controller, or the GUI, and how it works. And then let's jump over to the Arduino code. And in here, in the Arduino code, we first defined a bunch of pins and integrators, and for each of the axes there are different say new steps, previous steps, steps to go, all these sort of numbers that I use to calculate the speed and moves of the robot. But I'm going to skip over these, And I'll be publishing both of the codes underneath the video. So if you want to, you can check out this. And then we have the void loop. So the first part in here is actually reading the message that's coming to the Arduino from the serial, and it's saving it to a variable called data. And then if the data starts with the word drive, then you'd have, see in here, you'd have the J1 new steps, for example, and that's a certain substring of the data. And this would take all the values from the code that the Visual Studio sends over, and then just basically slice it to different pieces to get the steps or the information that you need, and then save it to a variable in here. And this all works, all of this data slicing works very similarly. So there's a drive option, then we have the calibration stuff, followed by the jogging. So if it starts with jog J1 minus, if it starts with jog J1 plus, etc, etc. So this goes on, and then we have so when you release the mouse button, it will send the word stop, and if the data is stop, then it would stop jogging all the axes. Right now, or actually in here it would set a J1 jogging to be false if it was true, and so on. And in here it would actually jog or just keep the axis steady. Right, so here we have the Arduino code for enabling. So this just read the word. So if data was J1 enable, for example, it would write the J1 enable pin. And the way it worked with these stepper drivers that I was using is that you'd have to write the pin low, low for the pin to be, or the stepper driver to be active, and high for it to be disabled. And then we have the enable all, disable all. This is where actually the hardest part of the code starts. So the drive program this is what I used to create the driving of the axis so that they would start and stop at the same time. We have the new steps and the previous steps variables that you saw up top, and it gets those values, so it remembers the last step, so where it actually is at a given time, and then when you get new information, so you get new data over the serial, so new position, it gets sliced to information so that each of the axes knows where it should be, and then it's calculating whether or which direction it has to move. So if the new steps is smaller than the previous steps, so if you give it a value to the robot on J1 is smaller than the current position, then it needs to go backwards, and if it's larger than the previous steps, then it needs to go forward. And then it will calculate a variable called J1 steps to go, for example, for the child one. And this would be, so if it needs to move backwards, this would be J1 previous steps minus the new steps. So say you're at a 0 position and you get minus 1000, then this if statement would be true. And since it's a minus 1000, you're moving backwards, right? And the new steps being minus 1000 is smaller than the 0 for the previous steps. So you move backwards, and then the steps to go is the previous steps. So 0 minus 1000. So this actually turned out to be a positive number, 1000. And that's exactly what you need when you're working with stepper motors, because you can't actually put negative negative values for the steps, since you have a separate direction pin which you need to write high or low depending on the direction, and then you just give the amount of steps that you want to move. So this way, through this code, you get to define the direction that you're moving, as well as the number of steps you need to take, and that number will always be a positive number. So let's take the next one. So this is for moving forward. So let's say that you're at 0 and you're moving the plus 1000. So you're moving forward to 1000. So J1 new steps being 1000 is larger or equal to the previous steps, which is 0. So that means we're moving forward. So the direction pin is 1. And J1 steps to go is new steps minus the previous steps. So 1000 minus a 0. So again, we're moving 1000 steps, but a different direction. And each of these values is, so we get the direction, J1 direction, or J2, J3, so on, as well as the J1 steps to go, J2 steps to go, etc. So we get the steps to go and the direction. Then we calculate the highest step. So we check which of these J something steps to go number is the highest. And this is, I'm trying to explain this the best way I can. It's been a while since I've actually looked through this code, but the way I did it is there's a resolution multiplier, and this was basically setting this would define how fine or how accurately the moves started and stopped at the same time. But increasing this number would actually result in a slower move. And I remember finding that 10 worked pretty well in terms of the speed and the accuracy. So what we would do is there's a J1 step skip, and what this bit of code does is it will calculate based on the highest step. So the highest step, say the J1, if it is the highest step, then the flow J1 steps to skip would be, say this has to move 1000 steps. Let's take an example. This is 1000 steps and the highest step, and the J1 is the highest step. So J1 steps to go is the 1000 steps, right? So then you get 1000 divided by 1000. So that would be 1 times the resolution multiplier, which is 10. And this would be the smallest step skipping number. And what this means is that so this number was 10, as we just calculated. And what this would mean that every 10th program loop, the J1 would take 1 step. Now let's take an example. So if J2 steps to go, if this was 1000, then the J2 steps to go if it was 500. Highest step, being the J1 step for 1000, would still remain 1000, but divided by 500, so J2 steps to go, which is 500, would equal 2. So this line here would be 2 times the resolution multiplier, so times 10, that would be 20. And the J1 steps to skip would take a step on every 10th program loop, as we calculated. J2 step skip, being 20, would take a step on every 20th program loop. And I hope you're seeing where this is going. So this being the highest step number, so 1000 steps, it would need to take the most steps in the given time frame for the moves to be stopping at the same time. So say this was 1000 steps, so it takes a step on every 10th loop. This is 500 steps, so it takes a step every 20th loop. So this would basically be moving twice as slow, but there are twice as few steps to take, or there are half as much steps to take. So that would basically result in the axis stopping and starting and stopping at the same time, but this one moving at half the speed. And this goes on for all the axes. So if this was 250 steps, or J3 was 250 steps, again, highest step would be 1000, and this would result in, this dividing would result in 4 times the resolution multiplier would be 40. So you would take a step on every 40th round, right? So that would move 4 times as slow, but it has 1/4 of the steps to take. So also start and stop at the same time. And that's what this bit of code actually does. And basically increasing the resolution multiplier in here, as I said, the higher I raise this value, so if this is times 100, so these all result in floating numbers. So right now in these examples, I'm using whole numbers, so integers, because it's easy for the calculation. But this could be anything. So say if it has to actually take like 1316 steps or something like that, and the highest step is, I don't know, 2000, that wouldn't result in a whole number. That would be like 1 point something, right? So the bigger the times value right here is, then the larger the number that, or when you multiply it, say if you, because in here we're making integers out of these float numbers. So if it's a resolution multiplier by 10, so if some of these numbers is say 1.5, it gets times 10, and you'd get 15, right? But say if it was 15.2, and you or if it was 1.52, and you timed it by 10, it would be 15.2, and then in here, where we're moving or converting these float values to integers, you wouldn't get the 15.2, but you'd get a 15. So it's actually losing some resolution on the steps, and this will cause the axis not to stop at the same exact time. But obviously, larger the multiplication number in here, the bigger these integers will be. So these step skips define how many steps or how many program loops a certain axis will skip before it actually moves or before it initiates, right? But obviously the Arduino is slow. So say if you raise this number to be 1,000, that would result in, say, the slowest axis or the fastest moving axis that has the most steps, that would be 1 from this dividing times 1,000. So the fastest moving axis would only move on every 1,000th of a program loop. So that would be too slow for the robot move. Right. All right. So so this is basically how I calculated the speeds of different axes so that they would start and stop at pretty much the same time. Or this was the easiest way around it, I thought. Right, then we're just writing the direction pins on the given directions, and these were calculated above when we were calculating the steps and whether we had to move backwards or forwards. And then basically what we're doing here is defining whether, so there's a common current step, kind of the current program loop that we're in. And then if this number is, or if this number divided by, say, a J1 step skip would result in a 0, so it would be divisible by this number. So that would result in a whole number. So basically, if the common current step was, say, if the J1 was the highest moving axis, and it would need to move every 10th program loop, then this common current step, when it's at number 10, so it has taken 10 program loops, then this if statement would be true. So 10 divided by 10 would result in 1, and it would be an integer number. So this would be true. And then if the J1 current steps, so where it's at, is smaller than the steps to go, so where it has to be, it would take a step and delay it by a couple of microseconds, and then write it low and add 1 to the current steps. Right, so this would just keep a log on where the axis is, and if it is the correct time for that given axis to move, then it would move it by 1 step and then add 1 to the current steps value. And this code just repeats itself over all the axes. Right, and then after all the program loops, we have J1 steps to go. That's been put back to 0, and the current steps back to 0. And the previous steps, equals the J1 new steps. So when you get a value and the robot has driven itself to that value or that position, those positions of the axis would become the new previous steps. So whenever the next one comes, you're already in a certain position, and based on that position you would calculate the next one, so where you need to go. So that's all the driving bit. And then here in the bottom we have the calibration stuff. So say if the joints are calibrating, so this would be a common value. So if any of the joints needs to be calibrated, this would be true. And so if it would be true, then it would check that if J1 is calibrated, if that's false, then it would move the axis, and this 20,000 right here, this is just a number. So when I start the robot, I'll move this YouTube video over. So when I start the robot, I usually start it at this kind of a position that you see on the screen, right? So for J1, for this rotation, 20,000 steps would be more than enough for the robot J1 axis to reach limit switch. So that's just a number I threw in. So it would move J1 for that amount, so basically forever, until it hit the limit switch. Once it hit the limit switch, it would break, and then it would turn the direction of J1 around, and then it would actually return. And we have J1 calibration return, so this is what I talked about earlier. So it would return from that calibration position a certain amount, so that it would be basically straight, so that it would be facing forward. And then it would write the enable pin low and do the actual moving in here. And this basically just goes on for all the axes, so this just copied and paste over. It's not actually been done until the end, so I only had the limit switches wired to the first 3 axes. So as you see, this, if J4 is calibrated, would need to be filled in with this kind of data as well, if I ever had it working. But unfortunately I stopped the project before I actually hardwired the 4, 5 and 6 axes on the limit switches. And after it's done the calibration, so whether it needs to calibrate all of them or just one of them, it would do it, and then it would set the joints calibrating back to false. Right. So this code would also would be running on the Arduino, and it would actually run the motor, and the Visual Studio GUI would be the one sending the information, so sending strings of words to the Arduino, so it would know what to do. And that's basically what I use to control the robot throughout the developing. And I hope this video helps someone if you are trying to do something similar, or if you're printing the robot that I have or wanting to control it somehow. And I will leave a file including both the Arduino and this serial port, this GUI program. But as I said, this is a kind of a raw software, so it's not really been tweaked and tuned very well. I'm not a software developer, as I said, so I did my best. But yeah, I hope this helps somebody and clears something out for you guys. So yeah, thank you for watching, and hopefully see you soon.